To identify battery cells, magnetic marker particles or fluorescence markers are used. The magnetic markers are produced from iron oxide using an industrial spray drying process. They can be added to either the electrode mass or the cell sealant. This enables the batteries to be read out contactlessly at a later stage. Fluorescence markers are produced using a sintering and washing process. This creates a crystalline powder that glows visibly under infrared light. These markers can be incorporated into the cathode mass or applied as an external tag to the finished battery. In the manufacturing of electrodes, the active materials are processed in an industrial production process. For this purpose, the material is coated onto a metal foil using a slot die and subsequently dried. These electrodes then form the basis for the actual cell production. Afterwards, they are punched to the desired size and automatically assembled into cell stacks. Separators keep the positive and negative electrodes apart. Once the cells are filled with the electrolyte and sealed, the finished batteries are created. All data collected during the manufacturing process is stored and deposited in the production system. This data can be retrieved later for the digital battery passport via the integrated markers. For this purpose, each cell is assigned a unique marker ID to enable identification and traceability throughout its entire life cycle. During the use phase, the batteries undergo many charge and discharge cycles, causing them to lose performance and age over time. When a cell has reached its end of life, it is first characterized and uniquely identified with its incorporated markers. Depending on the type of marker, this identification can be achieved either through magnetic marker particles and the readable code, or through fluorescent markers whose ID is optically recorded. The digital battery passport can then be used to retrieve information on the cell type, composition, and all relevant recycling information. The battery cells are sorted on this basis. In the example shown, this is done using fluorescent markers which enable individual identification. Each cell then enters the correct reprocessing cycle. The sorted cells are electrohydraulically shredded for recycling. This process uses shockwaves to specifically detach the coating from the electrodes, after which the material is separated into different fractions. The fractions are then separated using an automated, semi-continuous centrifuge system. An articulated robot moves the rotors between storage, the centrifuge, and the cleaning station. At the cleaning station, valuable materials are removed and the rotors are prepared for reuse. The water generated during the process is analyzed within minutes using lithium NMR. This enables a rapid evaluation of the feasibility and extent of lithium recovery. At the same time, the aluminum and fluorine content can also be determined with precision. In the final recycling step, the cathode material is re-enriched with lithium. This process, known as regeneration, involves a hydrothermal treatment followed by temperature treatment in a controlled atmosphere. The material is consequently restored to its original state. The recycling process is evaluated by examining its environmental and economic impacts. Areas with a particularly high environmental or cost impact are identified, and laboratory processes are scaled up and compared with current best practice. This information is then used to make battery recycling more sustainable and efficient.